Acids and Bases, Chapter 3. Objectives. 1. Acid and base definitions. 2. Acid and base strength. And 3. The effect of solvent on acidity. Your goals. By the end of the chapter, you should be able to determine if a species is an acid or a base and its conjugate, understand the use of curved arrows, know and understand the relationship between Ka, pKa, and acid strength and equilibrium, predict the relative acidity of uncharged acids by analyzing the conjugate base stability, predict the relative acidity of cationic acids, understand the solvent leveling effect. 1. Acid and base definitions. We begin with acids and bases to introduce the role of charges in ionic reactions. Most of the reactions we study in this course are ionic reactions, in which ions are either reactants, intermediates, and/or products. Key definitions. Acids and bases have two very important definition sets. The Bronsted-Lowry definition focuses on the proton, or H+ transfer. An acid is an H+ donor. A base is an H+ acceptor. Lewis' definition focuses on electron pair transfer. Acid is an electron pair acceptor, and base is an electron pair donor. We can see here that the donor of electrons is the base, in this case the water, and it's donating it to the B atom in boron trifluoride. Boron trifluoride is the acid. It is accepting that electron pair. Note that all Bronsted-Lowry acids and bases are also Lewis acids and bases, but the reverse is not true. In other words, there is no proton transfer in this example here, but it's still a Lewis acid-base reaction. We're going to focus primarily on Bronsted-Lowry, but we'll see Lewis as the semester progresses. For now, let's just focus on Bronsted-Lowry definitions. Conjugate acid-base pairs. Let's consider the Bronsted-Lowry example where we have hydrochloric acid dissolved in water. The acid is the proton donor and the base is the proton acceptor. But when we have the products are called the conjugates because now we have a new acid and base. A conjugate acid results when a base accepts a proton, and a conjugate base results when an acid gives up a proton. So let's consider the reaction that we just saw earlier. If we have the acid hydrochloric acid and the base water, when the acid loses H+, it becomes a conjugate base on the product side, Cl-. When the base gains H+, it becomes hydronium on the product side and becomes a conjugate acid. Label the acid, base, and the conjugates in the reaction below. Let's begin with labeling the acid and the base. You can tell that this proton here is going to be taken by the oxygen here because it has a formal -1 charge. So if this is going to lose a proton, the water is the acid because it's a proton donor. If this alcohol that has been deprotonated, it's called an alkoxide. If this species here will accept it, it is going to be the base. So we have the base and the acid. When the base picks up H+, it becomes now the conjugate acid. When the acid loses H+, it becomes the conjugate base. The base, the acid, the conjugate acid because the base accepted H+, and the conjugate base because the acid gave up H+. Let's practice. Acid-base conjugate pairs. Predict the product of the acid-base reactions below. Try using curved arrows to show the movement of electrons. Label the acid, the base, and the conjugates. We're going to talk more about curved arrows in the next slide. And note, as a hint, that water is amphoteric. That means it can behave either as an acid or a base depending on what else is present in the water. Let's begin. Notice that there's a lone pair on the nitrogen that can pull off H plus from the water. When it does so at the same time, these electrons here that are making the sigma bond need to become a lone pair on the oxygen. We end up with these two products here, the protonated nitrogen and hydroxide. The base, therefore, is the first compound, while water is the acid. It is donating H plus. The conjugate acid looks like the base, except now it has H plus, and the conjugate base looks like the acid, but it lost H plus. Let's do another one. In this scenario, we have a nitrogen with a positive formal charge, so its hydrogen will be acidic, one of the two. The electrons from the O is going to pull off that H plus, and then the sigma bond will become a lone pair on the nitrogen. Let's show that with arrows. Next, we want to draw our products. Our products are going to be the deprotonated species here, and we're going to have hydronium here. Let's label our acid, base, and the conjugates. Since the first species was the H plus donor, this must be the acid, and since water is accepting it, this must be the base. On the product side, this first compound here looks like the acid minus H plus, which means it must be the conjugate base. And hydronium looks like the base, but now it has H plus, therefore it's the conjugate acid. Now for the curved arrows. When bonds break and form, pairs of electrons move, and we can show their movement with curved arrows. Consider the following generic acid-base reaction. The base has the electrons, and they're going to attack H plus. At the same time, the bond between H and A has to break because hydrogen follows the duet rule. So as one bond is forming, the other bond is breaking, producing the conjugate acid, BH, and the conjugate base, A minus. How are the curved arrows here different from the ones we use to represent resonance? Here, the curved arrows are describing the actual physical movement of electrons. The curved arrows show the reaction mechanism. Learning to draw mechanisms is one of the most valuable skills in this class. Let's practice curved arrows. Consider a specific acid-base example. We have a base and an acid, resulting in the conjugate acid and the conjugate base. We can say that the base attacks the acid. Note how the lone pairs on hydroxide are going and attacking that proton, while the sigma bond between the H and the O is becoming a lone pair onto the oxygen. The acid cannot lose its proton without the base taking it. All acid-base reactions occur in one step. The mechanism shows two arrows indicating that the two pairs of electrons move simultaneously. For example, before long, you're going to be drawing mechanisms like the one you're going to see below. For now, just worry about correctly using curved arrows to show the acid-base reactions. That is, the proton transfers or the H plus transfer. Let's identify those acid-base steps in the following mechanism. So here we have several different steps where we have an alcohol reacting and pulling off H plus from hydronium. As it's pulling off H plus, the sigma bond is becoming a lone pair. Then in the next step, we can see that we have this protonated oxygen species that can actually leave as water. When it leaves as water, that will result as a carbocation. When that happens, water can come in and pull off H plus. The sigma bond between H plus and the carbon becomes a pi bond, resulting in an alkene. Which of these steps were corresponding to acid-base? Look for the proton transfers. In the first scenario, the base is the alcohol and the catalyst hydronium is the acid. When water leaves, that is not an acid-base reaction. So we're going to go to the next part where the H plus is being pulled away from the carbocation, which means that's going to be the acid, H plus donor, and water will be the base. 2. Acid-base strength. Recall from general chemistry, how do strong acids and bases differ from weak acids and weak bases? Let's define and draw a picture. Strong acids. One that completely ionizes or dissociates in solution. Some examples include hydrochloric acid in water that will form hydronium and the chloride ion in water. And in terms of a picture, what that means is if we added HCl gas, which would be molecular, to water, which is also molecular, the hydrochloric acid components actually break apart into the Cl- and H+, and each of these ions gets solvated or surrounded by water, and it's stabilized by those interactions, water interacting with the ions, or the charged particles. The same thing is true if we have a strong base like sodium hydroxide. It will also dissociate or ionize and break apart into its ions in water. Strong acids, there's actually a very short list of them: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, chloric acid, and sulfuric acid. Strong bases include group 1A metal hydroxides, soluble metal hydroxide, and oxide compounds. That's because if they're soluble in water, that means they can ionize in water or break apart into its ions. Everything else that we see in terms of acid or base are weak. A weak acid or base is one that does not completely ionize in solution, and it stays primarily intact. In other words, it stays molecular. It doesn't break apart into ions. Instead, it interacts with water via intermolecular forces. For example, hydrofluoric acid in water does not break apart into hydronium and fluoride. For the most part, it stays intact as HF, surrounded by water molecules interacting primarily by hydrogen bonding. The equilibrium arrows indicate that partial ionization, but for this very specific solution, there is mostly HF and a little bit of hydronium and fluoride. That's going to be true with any weak acid or base. We have equilibrium towards the reactants. The strength of an acid or base is helpful to predict how reactions will progress. We will learn to do quantitative strength analysis by using pKa values to compare the strength of acids. We will learn to do qualitative strength analysis by comparing the general stability of structures, primarily of the bases, or the conjugate bases. Quantitative strength analysis. Use numerical data to compare how strong acids are. Let's review equilibrium constants Ka and pKa. If we consider an acid and add that to water, the ability of the acid to dissociate or ionize in water can be determined by taking a look at the equilibrium constant and setting that equal to the hydronium concentration times the anion concentration all over the acid concentration, HA, and the concentration of water. Since the concentration of water is pretty constant, we can multiply both sides by the concentration of water and get Ka. Then of hydronium times the anion all over HA. Ka is called the acid dissociation constant of an acid dissolved in water, or the reaction between an acid and water. It is a measurement of an acid strength, where water is the base. Ka values will range anywhere from 10 to the negative 50 to 10 to the 10th. Such super small and super large numbers can be very difficult to imagine and even hard to work with. If the acid is strong, let's think about the magnitude of Ka. Will it be a bigger than 1 value or smaller than 1? So remember the definition of a strong acid or a strong base. A strong acid is one that completely becomes ions in solution. So if we have a high concentration of A- and hydronium, that means we're going to have a large Ka value, because HA is going to be a very low concentration or even non-existent relative to our products. Let's go ahead and consider what happens if we take the negative log of Ka. Then we're going to get values that range from -10 to 50. The pKa is equal to the negative log of Ka. Will strong acids have a low or high pKa value? pKa values range from -10 to 50. The lower pKa, the stronger the acid. Table of pKa values and use. Let's consider the table of pKa values for several acids, ranging from like sulfuric acid to ammonium, in this case here. The higher that we have an acid on this list, the stronger the acid, but then note the lower the pKa. Each pKa unit represents an order of magnitude or a power of 10. For example, which is stronger, hydrochloric acid or sulfuric acid, and by how much? So sulfuric acid has a pKa of -9, hydrochloric acid has a pKa of -7. So the difference is an order of a magnitude of 2, which means 10 times 10, which means 100. So sulfuric acid is 100 times stronger than hydrochloric acid. More about pKa values. You can also use pKa values to compare the strengths of bases, because the stronger the acid, the weaker its conjugate base. So if we have a strong acid, like we see up here, these are stronger and these are weaker, the stronger the acid, the weaker its conjugate base will be. The weaker the acid, the stronger its conjugate base. There are more acids and pKa values in Table 3.1 and on the inside cover of your textbook. Equilibrium and pKa. With the relevant pKa values, you can predict which direction an acid-base equilibrium will favor. Consider the example that we see here. We have a base and an acid. The acid is water, then a conjugate acid and a conjugate base. If we're looking at the pKa's, we take a look at our acid and conjugate acid. The acid pKa is 15.7. The conjugate acid is pKa 18. Therefore, equilibrium is going to favor the weaker species. The higher the pKa, the weaker the acid. Equilibrium should favor the products. Why is the arrow then on top bigger than the one at the bottom? To help indicate that. Higher pKa means weaker acid. Weaker acid means more stable. It will stay intact. Let's consider another reaction. Consider this one here, where we have a pKa of 15.7 and a pKa of 50. Again, we're looking at our acid, the acid itself and the conjugate acid, and determining which of the two is the weaker acid or the more stable acid. If it's weaker, it's more stable, and that's going to be favored. In this case, we don't have equilibrium arrows, we just have a yields arrow because the difference is so huge. If we consider that difference in pKa's, we're going to say there's going to be 10 to the 34 more products and reactants, pretty much saying that we have almost no reactant left at all. It's probably so small we wouldn't be able to detect it. It's not really much of an equilibrium and more like an irreversible reaction. This reaction demonstrates what has always been true in an acid-base reaction. Equilibrium favors the weaker acid and the weaker base. Qualitative acid-base strength analysis. To determine the relative strength of two acids without knowing their pKa values, we will compare the stability of their conjugate bases. The stronger the acid, the more stable its conjugate base. When an acid loses H+, it forms a conjugate base, which has a lone pair of electrons that resulted from the loss of H+. To determine the stability of a conjugate base, we are actually looking at the stability of the lone pair. Formal negative charge can affect stability. The more effectively a reaction product can stabilize its formal charge, the more the equilibrium will favor that product. Which acid is stronger and why? HCl or 1, 2, 3, 4. This is butane. Consider what happens when H plus is lost in both cases. We will end up with Cl minus and a carb anion. Cl minus can hold that negative charge a lot better than carbon can, so HCl should be the stronger acid. Well, HCl, because it's conjugate base, Cl minus, it's much more stable than butane's conjugate base, the carb anion. We can also use ARIO or ARIO to help us remember the stabilities when we're looking at them qualitatively. Atom, resonance, induction, and orbital. The more effectively a conjugate base can stabilize its negative charge, that is a lone pair, the stronger the acid. What factors affect the stability of a negative charge? The type of atom that carries the charge, resonance, induction, and the type of orbital where the charge resides. These factors can be remembered with the acronym ARIO or REO. Let's begin with A, the type of atom that carries the charge. Let's compare the acidity of the two compounds, butane and propanol. We need to draw and then analyze the stability of the negative charge on the conjugate bases. In other words, remove H plus and see what the conjugate base looks like. If we remove H plus from butane, we're going to have a carb anion, and if we remove H plus from the alcohol, we're going to have an oxide ion. When moving down a column of the periodic table, size is the most important factor. The larger the atom, the more stable a negative charge will be. For atoms in the same period or in the same row on the periodic table, electronegativity is the most important factor. In this case, C and O are in the same period. They are similar sizes. Therefore, the more electronegative atom will better stabilize that negative charge. And that will be the O, because O has a greater electronegativity when we compare it to carbon. That then results in a more stable conjugate base here, meaning propanol is a stronger acid or it's more acidic. Butane, having a less stable conjugate base, would then be less acidic. You can look up the pKa values for similar compounds and then verify your prediction. Now let's go ahead and consider R, resonance. Resonance can greatly stabilize a formal negative charge by spreading it out into partial charges or spreading it out more so more atoms can help out stabilize. Compare the acidity of the two compounds below by comparing the stabilities of their conjugate bases. We have ethanol and we have acetic acid. Let's remove H plus and consider what the conjugate bases look like. If we have conjugate bases, we're going to see a very localized negative charge on the O here, but here that resonance structures can help spread out that negative charge. We're comparing the stabilities then of these conjugate bases. Charge is localized, charge is delocalized, meaning this is going to be more stable. If this conjugate base is more stable, its acid that it came from is the stronger acid. So those results in an acetic acid being more acidic and ethanol being less acidic. Now we know the relative stability of the acids, and we can confirm this by looking up their pKa values. Now let's move on to I. I represents induction, and induction can stabilize a formal negative charge by spreading it out. Induction is different from resonance. Electron withdrawing atoms or groups will inductively withdraw electron density from the surroundings, thus stabilizing a negative charge. More electron withdrawing groups equals more stable conjugate base. Remember that electron withdrawing groups will have atoms that are electronegative, can pull electrons towards themselves more. The closer the electron withdrawing groups are to that negative charge, the more stable the conjugate base. Let's compare the acidity of the compounds below by comparing the stability of their conjugate bases. Does induction play a role? Well, in all of these four scenarios, we have the carboxylic acid, so resonance is definitely going to be in play once H plus leaves each one of these. So we're going to have resonance here, 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 and here. But if we consider nearby electron withdrawing groups, in this case the chlorines, the first structure does not have any, but the second one has one, the third one has two, and the fourth one has three. So the last one has many nearby electron withdrawing groups where electron density can be pulled towards them, but not via resonance, more as a pull and helps stabilize that charge. So this one here is going to be our strongest acid because it has the most stable conjugate base. And this one here is going to be our weakest acid because it has a less stable conjugate base. And we can check pKa's in order to verify 4.75 versus 0.70. Note the pKa differences. Now let's consider the O, orbital type. The type of orbital also can affect the stability of a formal negative charge. The closer the electrons are held to the nucleus, the more stable they are. The shorter the atomic orbital, the closer to the nucleus. The more S character, the more stable the negative charge. Best at stabilizing electrons will be the lowest in energy sp and lastly sp3. sp has more S character, 50%. In sp2, it's 33%. In sp3, it's 25%. So notice that sp being the shorter and higher percent S character would stabilize that negative charge the best. Compare the acidity of the compounds below by comparing the stabilities of their conjugate bases. How does the type of orbital play a role? Consider ethane, ethylene, and acetylene. In each case, if it loses H+, we're going to be left with carb anion. The first one will have a carb anion at this carbon here, let's say, this one here, and this one here. So if we have a carb anion that forms in an sp3 hybridized carbon versus an sp2 versus an sp, the one that's in the sp is going to be the most stable. Therefore, acetylene will be the strongest acid and ethane the weakest. Note their pKa's and the huge differences between them. Ethane has a pKa of 50, while acetylene has a pKa of 25. It is a much stronger acid relative to the other two. Let's practice. When assessing the acidity of protons, we generally use ARIO as our order of priority, or ARIO. 1. The type of atom that carries the charge. 2. Resonance. 3. Induction. And 4. The type of orbital where the charge resides. Now let's consider which H is more acidic. Is it going to be the one that's red, that's attached to the alkene, or the one that's in blue, that's attached to the alkyne carbon? Well, in both cases, we're going to be left with the carb anion when H+ leaves. However, with this one here, the carb anion will have the negative charge in an sp2 hybridized orbital, while this one will have it in an sp. The sp can stabilize it better, so that means the blue one is the more acidic one. Which acid has a more stable conjugate base? Ethanol or propylene? Well, in this scenario, if we have H+ leaving, we're going to have the negative charge on either O or carbon. O is more electronegative and can hold on to that negative charge better, so it's going to be ethanol that has the more stable conjugate base, which means it is going to be our stronger acid. Let's predict which proton, red versus blue, is more acidic in each of these compounds. Let's start with letter A. Is it the red one or the blue one? Again, in this case, it's a type of atom. O versus C. O is more electronegative, and therefore the one in red is going to be the more acidic one. Let's take a look at B. In terms of B, both H's will leave behind a carb anion once they leave as H pluses. So if we have a carb anion here and one here, that negative charge is going to be stabilized by resonance, and in this case here, by this O here, in this case by the two O's. Therefore, the one in red is more acidic because the conjugate base at this point is going to be the most stable. And now let's consider the H here that's in red attached to the O, and the H here that's attached to the N in blue. Since O is still more electronegative than N, the one that is red is going to be the more acidic H. It is typically helpful to use this in order of the priority list 1 through 4 when comparing the stability of conjugate bases, but it isn't 100% reliable and there are exceptions. Exception example. ARIO is a good general guideline, but it sometimes fails. In the following example, we know equilibrium lies to the right because we know the pKa values. Here we have acetylene reacting with the amide. When they undergo a reaction, we end up with the carb anion and ammonia. The lower the pKa, weaker the acid and the more stable, so we know equilibrium will lie to the right. Make sure that you know this exception. This is a very important reagent set. If we had judged the conjugate base stability using ARIO, we would have concluded that the negative charge on N is more stable than on C, and predicted equilibrium would lie to the left, which means the reactants, and we would have been wrong. Conclusion, for some acids, we simply just need to know the pKa values because there are exceptions to the ARIO priority rule. Using pKa values, you can never go wrong. But this is a very important exception. Make sure that you know it, that equilibrium will lie to the right. Predicting equilibrium. Consider any acid-base reaction, HA plus base yields the conjugate base and the conjugate acid. If pKa values are known, they are a surefire way to predict the position of an equilibrium. If pKa values are not known, relative stability of the conjugates should be used. Therefore, there are two distinct ways to predict which side is favored at equilibrium. 1. Use the pKa values of HA and HB. The higher the pKa value side will be favored. Or 2. The relative stabilities of the bases B- and A-. The most stable of the bases is going to be the side equilibrium will favor. In the reaction below, reactant or product is favored. Well, we're not being given the pKa, so we're going to go ahead and consider the stability of the bases. So I note that my base is right here, and my base is right here, because the nitrogens on both cases are holding on to that negative formal charge, or that lone pair of electrons. So since it's the same atom, we know we're not going to use the atom type. But now we're seeing that resonance can contribute an O here and an S here to help. Since S is bigger than O, that means S can hold on to that charge a bit better than the O can. They're in the same column. Therefore, this is the more stable base. Equilibrium will favor the reactant side. Reactant is favored because the negative charge is shared over an N and an S rather than an N and an O. Sulfur as a larger atom can stabilize a negative charge more effectively. Selecting reagents, acids. When we choose an acid that can effectively protonate each of the following molecules, we have to consider what is the pKa value of each. So consider this carb anion, and because acetylene has a pKa, or the protonated form, has a pKa of 25, we need an acid with a lower pKa. Any acid from the table with a lower pKa will do. How about this guy here? We have a carb anion. In this case, we have it on an sp3 hybridized carbon, which can also be stabilized via resonance. In this case, the pKa of acetone is 19.2. That's the protonated form. So an acid with an even lower pKa will protonate this deprotonated acetone. Now let's consider this species here, where we have the negative charge on an oxygen, but again is stabilized via resonance. This is the acetate ion, or the deprotonated form of acetic acid. The pKa of acetic acid is 4.7, so to protonate it, we need an acid with a lower pKa. And then here is a ketone. This is acetone. The pKa of protonated acetone, so we want to add that H plus here, is negative 2.9. So only an acid with an even lower pKa can protonate acetone. Three, the effect of solvent on acidity. Another important skill is to be able to choose an appropriate solvent for an acid-base reaction. The solvent should be able to surround the reactants and facilitate their collisions without itself reacting. Water is a very common solvent. Because water can act as an acid or a base, it has a leveling effect on strong acids and bases. Acids stronger than hydronium cannot be used in water without reacting with water. And bases stronger than hydroxide cannot be used in water without reacting with water as well. The leveling effect. Water and strong acids and strong bases. Acids stronger than hydronium cannot be used in water. For example, water will react with sulfuric acid, producing hydronium. Virtually no sulfuric acid would be remaining if we wanted to have it available to react with another reagent. Notice that the lower the pKa, the stronger the acid. This would favor the product side. Bases stronger than hydroxide cannot be used in water. For example, we wouldn't be able to perform the following acid-base reaction because the negatively charged amide species here would immediately react with water and not remove H plus from our sp hybridized carbon. Leveling effect. When to use water. Appropriate use for water as a solvent when the base is not stronger than hydroxide. For example, with water as a solvent, acetate ion will react with water, but equilibrium will greatly favor the left side, so water is an appropriate solvent. Note the pK in this case of water, 15.7 or 14, is a lot higher than the pKa of acetic acid of 4.75. Leveling effect. REO might not be enough. When acid structures are very similar, and REO cannot be used to explain the pKa difference from time to time. For example, let's compare ethanol and tert-butanol. Both of these alcohols would have the negative charge very localized on O when H plus is removed. pKa of tert-butanol is 18, pKa of ethanol is 16. That's telling us the acidic strength of ethanol is 100 times more strong. With all acids, the difference in acidity is due to the relative stability of their conjugate bases. The ability of the solvent to stabilize the conjugate base will come into play in this example. This is called solvating effects or sterics. This is the spatial arrangement of the atoms. The solvent must form ion-dipole attractions to stabilize the formal negative charge, or it must surround that negative charge. If the tert-butoxide is sterically hindered, it won't be well solvated as the ethoxide. That is why T-butanol is not as acidic as ethanol. The solvent can't stabilize it. So tert-butoxide is not as easily surrounded as ethoxide would be. And don't forget, counter ions are present. Counter ions, we also can know these as spectator ions, are not partaking in the reactions themselves, but are there to help counter the charge. They will always be present because they are necessary to balance the overall charge of a solution. Full reactions with counter ions included. Notice here we have sodium amide in water, making ammonia and sodium hydroxide. If we do not include the counter ions or we remove the spectator ions, we end up with the reactants and the products that will come into play for the reaction. Just don't forget, it's not just happening between a negative side making a negative side. We also have the sodium ion as a spectator ion that is balancing or countering that charge.